Hi everybody. In this video we're going to continue with Chapter 5, Proofs, specifically with Section 5.3, Indirect Proofs. And we're going to start with proof by contradiction. So one of the forms of indirect proofs is the proof by contradiction. In a proof by contradiction, to prove that some statement P is true, we instead assume that P is false, then proceed to derive an impossible statement, a contradiction. This means that P cannot be false, and therefore P must be true. Suppose we want to prove that a statement P is true. Furthermore, suppose that we can find a contradiction Q such that not P, then Q is true. But because Q is false, but not P, then Q is true, we can conclude that not P is false, which means that P is true. So this is in words what you can see here in this truth table. So now we're going to show you a few examples. So we're going to begin with example 5.15, and it says, consider the real numbers m and n. Prove that if m is rational and n is irrational, then m plus n is irrational. So the first thing you have to do is state that you're going to make a proof by contradiction. And then from here, you have to assume something, right? You're going to assume that there is a rational number m and an irrational number n such that m plus n is rational. Then that means that m plus n is going to equal some p over q, where p and q are integers and q is different from 0. Then we said that m is rational, so m is in the form r over s, with r and s belonging to the integers, and s is different from 0. Therefore, we have that m plus n is equal to p over q, and this implies that n is equal to p over q minus r over s, because we said that m is r over s. But this is the same as saying p times s minus r times q over q times s. But notice that p times s minus r times q and q times s are integers, since we already stated that p, q, r, and s are integers. Therefore, n is rational, and this is a contradiction. So next we're going to do example 5.16, and it says, prove that square root of 2 is irrational. So again we say by contradiction, and then assume square root of 2 is rational. So if square root of 2 is rational, it means that it can be expressed in the form square root of 2 is equal to m over n, with m and n being integers, and then n not being equal to 0. Then we also have the fact that m over n is irreducible. Okay, so then that means that the square root of 2 squared should equal m squared over n squared. And this implies that m squared is of the form 2 times n squared. Therefore, m squared is even. That means that m is even. Remember, we proved this earlier. M is even. Thus, m can be written in the form 2k for any integer k, right? then that also implies that m squared is equal to 4k squared, right? I'm just squaring this expression. And then this implies that 2n squared, which equals m squared, is of the form 4 times k squared, which means that n squared is equal to 2k squared. So n squared is even. Therefore, n is even. So what this implies is that because m and n are even, they have a common divisor, which is 2. Therefore, m over n is not irreducible. And this is a contradiction. So next we're going to do example 5.17, and it says, prove that for n belonging to the integers, if 3n plus 2 is odd, then n is odd. So again, we say by contradiction, and we're going to assume that 3n plus 2 is odd, but we're going to assume that n is even. Now, since n is even, it can be written in the form 2 times k for any integer k. Thus, 3n plus 2 is going to equal 3 times 2k plus 2. But notice that we can rewrite this as 2 times 3k plus 1. Therefore, 3n plus 2 is even. And this is a contradiction. So next we're going to take a look at proof by contrapositive. A useful type of indirect proof is known as proof by contraposition. Proofs by contraposition make use of the fact that the conditional statement, if P then Q, is equivalent to its contrapositive, if not Q, then not P. Another important thing is understanding certain statements, quantifiers, like this one, the universal quantifier. So it's this letter A that is backwards. It's read as for all, any, or for every. Then we have the existential quantifier, which is this letter E backwards, and it is read as there exists or there exists at least one. For example, for all real numbers n squared is greater than or equal to n can be written this way. Or there's an integer smaller than pi can be written this way. So now we're going to take a look at example 5.18, and it says, prove that for any real number x, if x squared is irrational, then x is irrational. So we're going to prove this by contraposition. So we say by contraposition, assume x is rational. Therefore, we can write x in the form p divided by q, with p and q belonging to the integers, and q is different from 0. So x squared is going to equal p squared over q squared, and by definition, p squared and q squared belong to the integers, and q is not equal to 0. Since the contrapositive is true, then the statement itself must be true. So next we have example 5.20, and it says, prove that for any two integers, m and n, if m plus n is odd, then exactly one of m or n is odd. So notice that this would be P and this would be Q in the conditional if P, then Q. So then what we're going to prove is if not Q, then not P. So notice that not Q is going to be M and N are both even or both odd. Then not P would be the statement, the sum M plus N is even. So we're going to prove this by contraposition. We say by contraposition, first let's state that R and S are integers. And we have two cases. Case one would be let M equal 2 times R and N equal 2 times S be even. Then M plus N is equal to 2 times R plus S is even. Case 2, let M equal 2R plus 1 and N equal 2S plus 1 be odd. Then M plus N is equal to 2 times R plus S plus 1 is even. So the contrapositive is true. Hence, the original statement is true. So next we have example 5.21, and it says, prove that for all integers a, b, and c, if c does not divide evenly into a times b, then c does not divide evenly into a, and c does not divide evenly into b. So notice that this would be p, and this statement over here would be q. Now notice that this statement here is of the nature a and b. The negation of this, according to Morgan's laws, is not a and b, which is equal to not a or not b. So by contraposition, we say, if c divides evenly into a, then a is equal to n times c for some n belonging to the integers. And AB is equal to NCB, which is equal to C times N times B. Likewise, if C divides evenly into B, then B is equal to M times C for some M belonging to the integers. And A times B is going to equal A MC, which is equal to C times AM. Therefore, we have proven the result by contraposition. So next we're going to do example 5.22, which will be the last one on this video. And it says, prove that for x belonging to the integers, if x squared plus 6x minus 5 is even, then x is odd. So we're going to prove this by contraposition. Assume x is even. That means that x is in the form 2k for any integer k. So x squared plus 6x minus 5 is going to equal 4k squared plus 12k minus 5. But notice that we can rewrite this as 2 times 2k squared plus 6k minus 2 minus 1. This is of the form 2n minus 1, and hence an odd number.